Welcome back to our second video here on our series dealing with the cubic equation of state. And in the last video, we began to talk about what the equation of state was and what van der Waals brought to the table, and talking about the compressibility factor and how gases behave when they are no longer behaving as ideal gases. And so in this video, what we're going to talk about is the generic equation of state, and what that is, a little bit of history and background on that, and then our goal by the end of the video is going to be taking it as a generic equation of state and expressing it in terms of the compressibility factor, and then talk about the reasons for that as well. So first, dealing with the generic equation of state, what happened was after van der Waals published his findings, and it was a really big deal in being able to show as a reality that can be taken as the compressibility factor and as that ratio for any and all gases, which is an incredible find. People went along and did additional experiments to see if they could make it more accurate, and sure enough they could. And so by just additional research and experiments, they were able to bring additional parameters to the equation to make it even more accurate than what van der Waals originally proposed. And so that leaves us here with the generic equation of state. And then here we've got V expressed 3 times in the denominator, and so if we were to multiply it out, it would be volume cubed, which gives us our cubic part of the cubic equation of state. And so now the reason for wanting to then change this expression into terms of the compressibility factor is because oftentimes we'll know the pressure and we'll know the temperature, but we won't know necessarily what the volume is, and we want to find that respective volume for whatever temperature and pressure the gas is currently at. And if we know the compressibility factor, or if we have things expressed in terms of the compressibility factor, then we'll easily be able to know the volume, because once we know the pressure and the temperature and the compressibility factor, and we'll already know R, then we have everything we know to know what the respective volume is at those pressures and temperatures. And so let's go ahead and work that out now. And so we're going to flip back and forth here. We've got our pressure, and we're going to just copy this over here, equals RT over V minus B, and then minus A with respect to temperature. So we'll just leave the temperature out. We're just going to express A here. Minus A, V, and then, we're going to bring in the epsilon and the sigma, talking about the additional parameters. This is the one that we're going to write in here. So let's go ahead and get that in the volume, and then that's going to be volume plus epsilon, and epsilon is multiplying by the excluded volume, so B is our excluded volume there, and then again the specific volume that we're trying to find, sigma times the excluded volume. And so just quick to point this out again, the identity or tendency that a molecule will take, the tendency that molecule spontaneously induces a dipole-dipole interaction, which is what is causing the van der Waals forces. And so the more it happens to induce spontaneously a dipole-dipole interaction, the more van der Waals forces it's going to have. So that's what A is talking about there. So let's go ahead and move forward from here. And now what we want to do is go ahead and get this whole equation with respect to the compressibility factor. And so again, if we remember, Z, the compressibility factor, does equal PV divided by RT. And so let's go ahead and multiply this equation to get this as Z. And so what we'll do is multiply both sides by V, the volume, over RT. And then that is going to get us to, that will bring us to the left side being Z, and then we'll have V over V minus B with the RT's canceling out. Then here we're going to have A times V divided by RT, and then rewrite this all the way out. Don't need that. There we go. Okay, so now we have this written out, but these volumes are a bit tricky to have some in the numerator, some in the denominator, and so let's go ahead and fix that. So what we're going to do is divide the numerator and the denominator by V, by volume, which is going to leave the left-hand side the same because that's just multiplying it and dividing by the same by 1. So now we're going to have 1 over 1 minus B over V minus A over RT over V, volume again. Now we were only able to do it once because we've got V squared, we got V happening twice in our denominator on the right part of the equation here. And so now now we're stuck. Oh, I need to bring this down. Apologize for that. We've got our one volume in the denominator and this expressed up here. So let's go ahead and take this right here, this whole side, and do the same thing again. Let's divide the numerator and the denominator again by V. So we're dividing by V. So that, let's go ahead and it's going to bring us to the next thing here. All right, back up, which leaves us with Z equals 1 over 1 minus B. Over 1 minus B. Then we've got, let's bring that V to the bottom. Put it next to RT. Okay, here we go. So now we're going to have 1 plus epsilon B over V. 1 plus sigma. It's a bad sigma there. But sigma nonetheless, it's not a 6. And then, so now we have still a bunch of V's sitting in our denominator. So let's go ahead and use substitution to get us to simplify this further. So knowing that Z equals PVRT, right, we know that V equals RTZ divided by P. And also, if need be, 1 over V equals the reciprocal of that, RT over Z. So let's go ahead and now use substitution. Back in, let's go ahead and substitute V back in everywhere we see V here. Okay. And so that is going to give us a nice, it's going to keep fattening out this equation here. So now we've got a lot of values going on. We've got Z equals 1 over 1 minus BP RT Z minus, let's see here, we've got, well, let's see, we've got from here a V in the bottom, so A over 1 over V, so let's go ahead and substitute 1 over V here, and so that's going to then give us, let's bring the over V, which is going to leave us with minus there we go. Okay. would be, well, let me just apologize for that. Let me just go ahead and write this out. I was having a hard time visualizing that out for a second. So if it's A over V, it would be A over RT, Z over P, and then what we'd do then is bring this up and flip this around. Okay, there we go. So we've got AP over RT, Z, and then that whole thing is over RT and again, let's just go ahead and bring this up as well. So we'll just lump the RTs together, so that's going to be R squared T squared over Z. Now let's go ahead and just have our two factor terms here. So that's going to be substituting in our V still is going to give us 1 over epsilon B, and then it's 1 over V again. So now with the inverse, we're going to do P RT Z 1 plus sigma, it's better sigma that time, B, and then again the reciprocal of V1 over V, so we got P over RT Z. Okay, now thankfully we don't have to leave it like this. This is in one sense expressed in terms of the compressibility factor, but that's a lot of variables. And so we can simplify this further, because what we have here are terms that have already been expressed. And so we've got beta equaling BP over RT, and then Q equaling A with respect to temperature divided by B times R times T. And so that's going to allow us to plug these in, simplify our equation down, which is going to be nice. So let's go ahead and do that here. Okay, so let's bring this in. Here, sorry about that. Bring this over. Okay. Now, writing that back out again, Z equals, I don't want to write that all back out again. Let's see. So moving forward, we're going to bring the beta value and the Q value, and we're going to substitute that in because of what they mean respectively. So looking back here, we see that beta equals this. So let's go ahead and write that in here. Beta equals BP over RT, and then Q equals A with respect to T over BP RT. So now here is where we're going to be bringing in our beta and our Q values. So go ahead and do that now. Z equals 1 over 1 minus BP over RT Z minus A P R squared T squared Z divided by 1 plus epsilon times B times P RTZ RTZ. Okay, so now we can start making some substitutions in, which is going to leave us with Z equals, so here we're going to see a lot of BPs and RTs here, so let's just swap that out with a beta. So 1 minus 1 over minus beta over z. Now in this next column, we're going to see Q equaling A over B times RT. So if we take this expression right here, let's go ahead and take this. Let's bring this over here, unpack this a little bit and what's going on here. So we got A, P, RT, we got one RT, got another RT, and then we got a Z. And so, or we could even just say 1 over RTZ, because the fact that we've got our Q equaling this is going to leave us with, here we've got this right here equals beta divided by B. And then what we can then do is, so now we've got A over RTZ, and then B beta over B. Well, now we've got our Q. So this is going to then equal Q beta over Z. Okay, so now we can bring this back over here. So now we've got Q beta divided by Z, and then that's going to leave us with 1 plus, substitute that beta in, do the same thing again, it's showing up, there we go, 1 plus sigma beta over Z. Okay, now we're getting closer, which is great. And so now what we're going to then need to do is, if we take the inverse or divide by compressibility factor both sides, that's going to help us simplify this even further. And so now let's go ahead and see where that takes us. So that's going to leave us with a 1 on the left-hand side of the equation. And then that's going to give us a 1 over Z minus beta. And then that's going to leave us with Q beta Z on the outside. We don't want Z on the outside. Let me look at that again. Just Z, we'll have taken into factor it out here. So we've got Z plus epsilon beta. We've got Z again plus sigma beta, carrying the Z all the way out. Now, instead of having our volumes in the bottom and the denominator, we have the denominator expressed in terms of the compressibility factor. And so now what we can then do is just multiply, get like denominators, and simplify this all the way out to have Z expressed as a cubic polynomial. So let's go ahead and do that now, which means our left-hand side of the equation is going to be both denominators in order to get the numerator the same. So let's go ahead and write that out. And then that's going to then equal, so now we're going to get Z again plus sigma minus the QB, or Q beta I should say, C minus beta. And then let's go ahead and move this to the left-hand side of the equation and set this equal to 0. And in so doing, we me keep this on the same page here. But that's what we're doing here, getting this to set to 0. And then let's go ahead and make a chart. Keep all these factors. So anything with these as our coefficients. So z cubed as a coefficient, z squared. There we go. Then let's see, z, and then any factors that don't have z in front of them to multiply out. Okay, so we are moving this to the left-hand side, tracking our terms, only going to have one z cubed. Then have an epsilon plus a sigma multiplied by beta. And we're going to have a, let's see, negating go minus beta and then a minus 1. Okay, now moving to z, not z squared, but just z anymore. We're going to have more terms because they're going to show up more often. Multiplying this out, bring this down. We're going to have epsilon, sigma, beta squared. Then we're going to have minus beta squared times epsilon plus sigma. And again, these terms have, each of these terms are going to have these in front of it. So this has a z squared, this has z squared, this has z squared, and this has a z, this has a z. Then minus epsilon plus sigma times beta. What is our last term? With just a z, it's going to be a plus q beta because we're negating it. We're negating a negation because bringing it to the left-hand side. And then lastly, with nothing in the term, what's left here is going to be minus epsilon sigma beta squared. No, beta cubed. Then minus epsilon sigma now beta cubed. And then lastly, okay, then we've got lastly is minus q beta squared. And that, instead of writing all out, which we can if we needed to, but having it expressed here as a table allows us to be able to see what goes with which compressibility factor to what power for it. And so this is going to be our general cubic equation of state. Whether we went further and used the values respective for the SRK or the PR, here is going to be our generic equation of state expressed in terms of the critical compressibility factor, expressed as a cubic polynomial.